function, they both should have the same y-intercept. Okay. So if you look at the original, it would be 0 squared plus 6 times 0 plus 5 over 0 squared plus 3 times 0 plus 2. And that reduces to 5/2.
Right.
So the y-intercept is when x equals 0. And now the reasonable question is, all right, well, hey, Matthew, like, how did you figure that out? How did you know? Well, I took a guess that it was these last two numbers, that it probably worked out for these last two numbers.
Right.
Okay, and I mean, unfortunately it's hard to do because you're going backwards. You're not like given the y-intercept. So let's do this here. Let me give you an example problem here. Let's say that it is y equals x squared plus 3x plus 2 over x plus 4. What is the y-intercept for this problem? Can you tell me that, please?
It would be 2, 4, so it'd be 1/2.
Yeah, it would be 0, 1/2. Okay. And you get that from those last two numbers there, the ones on the end. So does that always work? Pretty much. So let's say I wanted this is where you're just really manipulating the numbers. Let's say I wanted it to be I want now the y-intercept to be 0, negative 4.5. Okay, and that's where it's almost better to turn this into a fraction. Can you tell me what that would be as a fraction? So the cheat or the shortcut here is to grab your calculator and plug it in minus 4.5 and then go math, enter on that. Do you have your calculator handy?
No.
Okay. Well, if you did, you would get negative 9/2. Okay. So you're looking for a function in the numerator that has a negative 9 or a positive 9, and then a function in the denominator that has a 2 or a negative 2.
Oh, okay.
So what would that be? What would go in the numerator based on that list? Do you have that piece of paper in front of you?
Yeah.
Okay. What would go in the numerator?
It would be x plus 4.
In the numerator? It's got to be either a negative 9 or a 2 in the numerator.
Oh, I'm looking at the wrong thing. It would be a negative 9.
Right, but what is the function? What is the full function from that list that you're given?
It would be x minus 3x plus 3.
Yeah, x squared minus 9, which what does reduce to that. Good. And then what goes on the bottom? Because you need a 2.
X plus 2, x plus 1.
Right, or the x squared plus 3x plus 2.
Yeah.
Okay, now this one's slightly more difficult. Okay, but it's kind of the same deal. Now we'll move to another problem here. Let's say the y-intercept is 0, negative 4 over 9. So you're looking for a function that has a 4 or a negative 4, and then over a 9 over a negative 9.
So it would be x plus 4, and then x minus 3 squared.
X squared minus 9.
9.
Because you got to get the 4 and the 9.
Yeah.
And so it doesn't matter that they're opposite in sign, because it becomes 4 over negative 9 for your y-intercept, 4 over negative 9, which is the same as negative 4 over 9.
Right. Okay.
All right, let's move on to this next one here, where where the limit as x goes to minus infinity 0, positive infinity 0. Okay, and x goes to 0 is 2. Okay, so the this is weird. I mean, it's really weird. It's creative. I mean, if I were giving the instructor feedback, I'd say, well, this is like more effort than most teachers put into their assignments. It's very confusing for a student.
Yeah.
So this business right here, this T20, I think, yeah, you said, okay, that's the y-intercept. The y-intercept is 2. Okay.
Yeah.
And that's almost like a cheat on this, because like, well, there's only 2 possibilities, or 1 possibility for it to go to 2. It's x plus 4 in the numerator. And I know you keep factoring it. I'm gonna look at the non-factored form, x squared plus 3x plus 2 in the denominator. That's the only way you get 2 as a y-intercept.
Mm.
There's no other ratio of 2 numbers, because you'd have to have, a 6 and a 3, or 8 and a 4. You'd have to have one number double the other. All right.
Right.
Is that clear?
Yeah.
Okay. So we should now actually review what it is for for first part of part B is this limit as x goes to infinity. So here's what this means. This means as x gets really large. Okay. And if you take calculus, you will learn how to do this officially, but there are 3 cases to consider. And it's based on the degree of the numerator. You probably saw this in class. That's thing 1. And the second thing, it's based on the degree of the denominator.
Right.
Okay, so case 1. So I use an N and a D to indicate the degree. Okay, so case 1, if N is less than D, and you're like, what does that mean? So let me give you an example. Okay, let's say it's x plus 4 over x squared minus 9. The degree of the numerator is 1, and it's the exponent of 1. The degree of the denominator is 2. It's the exponent of 2. Do you agree that the numerator is less than the denominator in terms of its degree?
Yes.
Okay. It is always the case that the limit as x approaches infinity of this, it always goes to 0. Doesn't matter whether it's plus or minus infinity, it always goes to 0. You might have previously seen this as a horizontal asymptote y equals 0.
Right.
So let me give you another one here. Let's give you another example. Let's say it's x squared minus 3x plus minus 4 over x cubed minus 1. This is f of x. What is the degree of the numerator? What is the highest exponent?
It'd be 2.
2. What is the degree of the denominator?
3.
Very good. Is 2 less than 3?
Yes.
Yes. So the limit as x goes to infinity, f of x is 0. The limit as x goes to negative infinity, f of x is also 0.
Oh, okay.
It is always, 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 always 0, no exceptions. But unfortunately, there's more than one case. So that's where they get you. They say, oh, you gotta learn a little bit more.
Okay.
Let's see here. So now let's go to case 2. Case 2 is when the degree of the numerator equals the degree of the denominator. Okay, so let's look at an example, because it's like, what does that even mean? It's like, let's look at an example. I'll actually give you something here. Let's say it's x squared minus 9 over x squared plus 6x plus 5. The degree of the numerator is 2 because of this exponent. It's always the exponent. The degree of the denominator is also 2. Okay. So now your limit ends up being the following of f of x. It's the, I'm going to write in words, the ratio of the leading coefficients. It's like, what is that? Well, it's the numbers in front of x, or x squared in this case. So there's a 1 and a 1. Ratio means you're dividing. It's 1 over 1.
Oh, okay.
But this is kind of a crappy example. Sorry, I shouldn't say that. Wow, that was bad. Okay, let's give you a better example. Let's say it's something like 9x squared minus 3 over 4x squared plus 1. Okay,
Mhm.
so this is another example. So the degree of the numerator is 2.
Yeah.
The degree of the denominator is 2. They are the same. If they are the same, it becomes the ratio of the leading coefficients. In this case, it's 9 over 4. And you can write it as a decimal if you want. Okay, so let me give you one more example before we move on to something else. This would be example number 3. Let's say f of x equals 1 minus 2x cubed over 16x cubed plus 1000 x squared minus 10 to the 1000 x. Okay. And you want to know the limit as x goes to infinity, plus or minus. It's the same in both directions, f of x. So it's still, the degree of the numerator is 3. The degree of the denominator is 3. You look at the highest degree exponent on x, not on this other business. This other stuff doesn't matter. It's totally irrelevant. It's distracting. You look at just the x. So since they're the same, it's the ratio of the leading terms. Now your leading terms are the coefficients in front of x. So it's -2 over 16. So it's not always the case that they're out in front. It's wherever the highest term is. So for you, this would be -2 over 16, which reduces to -1 over 8.
Okay.
All right, so now to do part C on your assignment, we need just a tiny bit more information. So how do we do this? Case number 3, let me do it this way. So case 3, this is the last case. Case 3 is when n is greater than d. Okay, and you're like, okay, well, what does that mean? Let's look at an example. Let's say it's x, let me go back and look at your functions. Let's say it's a x squared minus 9 over x plus 4. Okay, the degree of the numerator is 2, the degree of the denominator is 1. Do you agree that 2 is greater than 1?
Yes.
So the limit here, as x goes to infinity f of x, it either goes to plus or minus infinity depending on some other things, which we'll talk about.
Okay.
So what does Paige have to know? She has to know all 3 cases. She has to be able to know which case it is, and then you have to be able to apply it to the problem. You know, that is at the core of what you're trying to do here. So rather than like trying to do C, let me just give you a few more of these, and these are terrible examples. They're all the same. They're all the same. They don't help you. So let's look at one here. Let's look at the, let's say f of x equals x plus, sorry, let me not do that. Let's go x squared plus 6x plus 5 over x minus 2. What is the degree of the numerator?
2.
2. And is 2 degree of the denominator?
No, it's 1.
It's 1. So this is this third case. So it either goes to plus or minus infinity. Now we're going to talk about how you would know. Okay. So let's take a look at the limit as x goes to infinity, f of x. And we know it's either plus or minus infinity. So we'll put the infinity symbol there for the moment. So here's how you decide. You look at the ratio of the leading coefficients here, okay? And you also ask yourself, well, what happens when you put a positive number and square it? You get a positive number, okay? And since there's a positive 1 out in front, it's still positive. When you put a positive number in for x, it's positive. And when you multiply by 1, it's still positive. So you have a positive over a positive, which gives you a positive. So you have to do a little bit of analysis using, positive and negative. So now let's go the other direction. Let's say the limit as x goes to negative infinity. And if I need to clarify this notation, I can. This is a calculus concept, so you may just want to write it down and not think too much about it till next time, next math class you take. But if you need to, we can go through that. So when x goes to negative infinity, you're kind of looking at this leading term, x squared over x. You're literally looking at 1x squared over 1x, and you're like, what happens? Well, a negative number squared becomes a positive, and you're multiplying by 1, so it's still positive. A negative number in the bottom times 1 is negative. Positive over negative is negative. And that's how you decide.
Okay.
So it's not always the case that the positive goes to a positive, negative goes to a negative. These can be flipped, but it either goes to plus or minus infinity. Now, are you allowed to use? Do you think you'll be allowed to use your graphing calculator on this?
Probably.
So you could graph this, and if you get your window big enough, it'll shoot off to infinity. It'll shoot off to negative infinity, and you can do it that way.
Okay.
Removable and non-removable. Discontinuity. Okay. All right. So let's look at another example here. Let's say it's f of x equals 1 minus x to the 4th over 3x squared minus 2x plus 1. Okay, so if you were just given this problem on a test or quiz, you have to be like, all right, I got to figure out the numerator degree and the denominator degree. Can you tell me the degree of the numerator and the denominator?
3 and 2.
3 and 2. So we know it's a case number 3. We know that the numerator is greater than the denominator. So we know that it either goes to the limit as x goes to plus or minus infinity. It either goes to positive or negative infinity. So let's start with the positive infinity case. Okay, now your focus, and I'm doing this intentionally where I don't put it as leading term. Your focus is on this over this, the leading terms. So let's say it's a really big positive number. When you cube it, when you cube a really big positive number, you get a positive number, but then you have a negative out in front, so it becomes negative. Do you see that?
Yeah.
So you can pick a number if you want, negative 10 billion cubed, but then it's negative. On the bottom, you do the same thing. You square it. So you're squaring a positive number, so it's squared. It's positive. Times 3, it's still positive. So you have a negative over a positive. And that results in a negative. So this goes to negative infinity. So you can't just automatically be like, oh, if it's positive, negative, it's whatever it is. So now we're going to go to negative infinity. So you're doing kind of the reverse. You're like, all right, let me put in a really negative number in for x. Really negative number in for x. So when you cube a negative, it's negative times negative times negative. That produces a negative. But then this becomes positive. So the result is positive. In the bottom, you have a negative times a negative. That makes a positive times a positive is a positive. Positive over a positive is a positive. Now, if you don't like this approach, we can use your calculator to help by putting numbers in for X, but it's essentially the same thing. If you want to grab a TI-83, I can show you how to do that, or 84. If you don't, we can just move on.
Honestly, I think this would be best because I feel like I would mess up on the calculator.
Okay. Fair enough. So let me look here at your problem. Yep. Okay. Your answer to C is fine. Okay. So we're ready to move on to D. Move on to D. Do you have any swim meets coming up or swim season? Almost. What's going on there? Oh, you're injured. I'm sorry. You're still injured. I'm sorry.
Well, I am still swimming.
Okay.
I have a meet tomorrow and then I'm done in December.
Oh, nice.
Yeah.
So any college prospects, or is that still kind of
that's like 50-50 right now.
okay? All right. Okay, let's look at problem D. It says to create a rational function with a removable. It's like, what is that? And a non-removable discontinuity. So there's only one type of removable continuity. Discontinuity is a hole. A non-removable that you care about is a vertical asymptote. So the more traditional way of learning this is I give you problems with vertical asymptotes, I give you problems with holes, and then I mix them together and you get, a problem with both. And, for some reason they're mixing them together in one problem here. So I can't believe this. Are you in an honors pre-calculus class?
No.
Okay. All right. Maybe your teacher is honors. All right. Let's go. So let's go. The whole occurs when the factors in the numerator and denominator cancel.
Okay.
So that's why you had that factored form up above in this assignment. So that really helps here. Why did I bring that up? Because because x squared plus 6x plus 5 over x plus x squared plus 3x plus 2, these end up factoring and they have factors that cancel.
Right.
Okay, and that's huge because that's what you need for a hole. So wherever the factors cancel, you have a hole when x plus 1 equals 0. It's the factor that cancels.
Right.
So you solve that for x, you get x equals -1. But wait, there's more. Like you can't just say, oh, okay, that must be it. You have to find the y value. It's like, well, how do you find the y value? So to do that, you take that x value you just found and you plug it back into the reduced form.
Oh, yeah.
And that's what I think is sometimes unclear. So where do you put it? You put it back in the reduced form. Reduced form, not the original. The original won't help you. You'll get 0 over 0. So it's -1 plus 5 over -1 plus 2, 4 over 1, which is 4. That's your y value. Y equals 4.
Okay.
And so this is, and you graph as you go. You don't want to wait till the end of the graph. Graph as you go. Okay. So to do that, you go down to the graph, which I'm now making, and you go to, it's terrible, -1, 4, and you make a really emphatic, oversized hole. I actually saw this on something on social media. Some student and you probably try this, you know, I think we've all tried this, where you sort of make it look like it's both true and false. Don't do that. Try to just do it right and be over emphatic with your hole. Okay.
Okay.
All right. So that's the removable one. The non-removable one comes from the reduced form. So your reduced form function f of x is x plus 5 over x plus 2. So your vertical asymptotes occur where the bottom equals 0, where x plus 2 equals 0. So that's at x equals -2. And then you want to graph that also right away. So here you go, -2, boom, we got that. And this is a technique that I recommend. I like to put arrows around the asymptotes because we're going to connect the lines and the dots together.
Okay.
So now we've got to find the horizontal asymptote. So the horizontal asymptote, you look at the reduced form over here, and is it case 1? Is it case 2? Is it case 3? So notice that the degree of the numerator and denominator are the same. So since they are the same, it's the ratio of the leading coefficients, which is 1 over 1. So there's a horizontal asymptote at 1. Again, I like putting in these little arrows because we're going to connect some of them and it'll help us figure out what the graph looks like. But and there's sort of like what your instructor is going towards is there's like this, sometimes it's like 10 steps or 7 steps, and you're trying to figure out what the graph looks like. So you first find like domain, and then holes, and vertical asymptotes, and horizontal asymptotes, and there's a bunch of other things. And that's what we're doing here.
Okay. Got it.
So to finish off our graph, we need the y-intercept and the x-intercept. So let me write this down again. F of x equals x plus 5 over x plus 2. To find the y-intercept, you set x equal to 0. So that's 0 plus 5 over 0 plus 2, 5 over 2. So that's a point on the graph. It's 0, 2.5. Now this time it's not a hole, so you don't have to make it overly emphatic. You just got to like nice little dot there. Okay. And that helps to give us some idea of where to connect things. The next one we will do is the x-intercept. So the x-intercept is when you set the numerator equal to 0. So a lot of rules like how do you find a hole? How do you find a vertical asymptote? How do you find, what are the 3 cases? There's a bunch of rules. So you actually don't get very many questions on a test or quiz because they do take a long time. But you set the numerator equal to 0 and you get x equals -5. That's your x-intercept -5, 0. That's another point on the graph. So you go back up to your graph, 1, 2, 3, 4, 5, boom, there it is. And it's a connect the dots lines thing. Now, what you cannot do is you can't cross the dashed line. So the only way you can connect things is to stay on the sides of it. So there's a possibility. And this one here, this isn't to scale, but looks something like that. But to do this, you really need a bunch of things here. You need the hole, the vertical asymptote, the horizontal asymptote, the y-intercept, and then the x-intercept. And then there's another list of things if this gets even more complicated than this.
Got it.
So that is it. That is it for that part D on the question. Now we can move to the other page where it's got a bunch of questions. It's kind of the same thing. It's another problem with a lot of steps. So we can look at that. See if we can get through both of these. All right, so what is the first thing that it asks for in this laundry list of things? Zeros. So that's actually wrong. We should not be doing that first. Why did they do that? You cannot do zeros first. So don't do that. That's completely wrong. First thing you want to do is factor. And this is where, you know, prerequisite skills really matter here. You can factor a -3 out of the it looks like you did that actually nicely in the work there. X minus 1, X plus 1, and then the bottom, yeah, it's X minus 3, X minus 1, X minus 3. I'm just going to reorder it X minus 1. Okay. So actually the first thing you do is domain. Okay, and you get domain by setting the denominator equal to 0 at the start.
Okay.
We will answer all your questions, but let's do it in the right order. You know, it's like you're trying to swim before you jump in the water here. It's really bad, really bad. Okay, so the denominator equals 0. You could set the original denominator, but we factored because it's like, yeah, it's a lot easier to do that. So that's X minus 1, X minus 3 equals 0, and you set each of those equal to 0. So X cannot be 1 and X cannot be 3 because you're never allowed to divide by 0. All right, so your domain, if you think of your domain as a number line here, here's 1, here's 3, here's -infinity, here's infinity. It's everything but those points that you're allowed to be.
Right.
Okay, and this is -infinity to 1, union 1 to 3, union 3 to infinity. All right, the second thing you find are holes. Second thing you find are holes. So holes are where the numerator and the denominator cancel. You can see now that there's a hole because X minus 1 cancels, and that is what you set equal to 0. There's a hole at X minus 1 equal to 0, which is X equal to 1. So you have to cancel those out. And then I got to grab this so we can work with it down below. It's not good. Okay, right there. Okay. Got it here. So the reduced form is -3 X plus 1 over X minus 3. So to find the Y value, because you really need it, you take that 1, you plug it in there, and then there. So you get -3, 1 plus 1 over 1 minus 3. -6 over -2, which is 3. And that's a discontinuity. So so there's a discontinuity at 1, 3, and you want to say what it is. It's a hole.
Right.
And if you want to know why it's removable, because they may ask you on a test, it's because you can fill in a hole. If you make a hole, you fill it in. But there is a second type of discontinuity that you might find. That's number 3 here. Those are vertical asymptotes. Okay. And that's where you look at the reduced form. So you're looking at this reduced form here of the function. And that's where you set the it didn't work out. That's where you set the -3x plus 1 over, no, that's not right. Yeah, it is, over X minus 3. You set the bottom equal to 0.
Okay.
So you get x equals 3 is a vertical asymptote. This one is not removable. You can think of it as a river, like a river. You can't remove a river. I know there's dams, but just the analogy doesn't work great for everything. Can't fill in all holes, but most of them you can. So it's not removable. And this is where we probably would like to start graphing some of these things. We should do that. We should do that. So x equals 3 is a vertical asymptote. So something like that, little dashed line, some arrows. The hole is at, what did I say, 1, 4? 1, 3, 1, 3. 1, 3, nice big emphatic hole. Okay. All right, and so we've done discontinuities. We will get back to zeros. We're going to do end behavior next. End behavior is really horizontal asymptotes. Horizontal asymptotes are the exact same thing as end behavior. And so you use the reduced form. Use the minus 3x plus 1 over x minus 3. And you can even multiply in. That's actually probably a good thing to do here. And you need to decide what case is this. Is it case 1 where the numerator is less than the denominator? Is it case 2 where the numerator is equal to the denominator? Or is it case 3 where the numerator is greater than the denominator?
It's case 2.
It's case 2. So in case 2, it's the ratio of the leading terms. Minus 3 over 1, which is minus 3. And you draw another line there. We should label the lines so you get full credit. I like to put in the arrows because we'll connect them later on. So that's your end behavior.
Okay.
We'll get to middle behavior here shortly. So the next thing is the y-intercept. Y-intercept, that's when you set x equal to 0 in the reduced form. So notice you use the reduced form after you find holes, you just stick with it. You don't have to go back. But you got to find holes first. You can't wait till the end because then you mess it up and you miss a bunch of other stuff. So we have minus 3 x minus 3 over x minus 3. You put in 0 for x. So you get minus 3 over minus 3, which is 1. So it's the ordered pair 0, 1. And that is not right. Did I mess up something? Oh yeah, I wrote the wrong function.
Oh.
Did I? 0, 1. Oh no, I guess that does work. I'm sorry.
It's okay.
Never mind. It does work. Okay. Ooh. All right. So that is your y-intercept box. And then number 6, it says zeros. There could be more than one. You can think of these as your x-intercepts. And this is when you set the numerator equal to 0 of the reduced form. So you set that minus 3x minus 3 equal to 0. And you solve for x. So you get minus 3x equals 3, x equals minus 1. So there's your x-intercept, minus 1, 0. Go back to your graph. There's another nice dot. So as I mentioned before, you cannot cross the fence, the dashed lines. Think of them as property fences. And again, it's just an analogy, but you generally don't want to do that. So the only ones that can connect are the arrows where you're not crossing. And that gives you some insight. And then it's always in the opposite position for these types of graphs. So it looks something like that, not to scale, of course.
Okay.
So we have not done middle behavior. It's Weird. Weird. Middle behavior. Can't even believe I'm seeing this. So the middle behavior, they're asking what's happening around the asymptote, the vertical asymptotes, because there could be more than one. Let's see if your next problem has more than one. Maybe. Yeah, your next one might have more than one. So they're basically asking what is going on as you approach 3 from the left and then from the right. And this is a calculus concept, but they're trying to show you this in your pre-calculus class here. So let me see if I can very carefully snip this so we can look at it and have a little more work space here. All right. Okay, so the first thing you're trying to do is find the limit as x approaches 3 from the left. So this right here, this minus when it's to the right of the number, means from the left. So you have left, you look at the graph. Okay, from the left means I'm coming from the left and I'm approaching it from the left. So how far up does this go when you come from the left? How far up does your y value go?
It goes up
How far up does that go?
To like, oh God, I don't know.
Infinity. Goes up forever. So the answer to these questions about the middle behavior is generally infinity or negative infinity. So if I were there, I would have you like put your finger on the curve and trace it, and then like keep watching go up and 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 up, and you would say, oh, it goes to infinity. It doesn't work as well in this format for that, but you get the idea. Now the limit, the other limit is the limit as x approaches 3 from the right. So this positive means from the right. So I might even ask my instructor, hey, this is a calculus concept. You don't have to say that I said it. You can just say, hey, I was looking, these are under calculus concepts. Like, why are we learning this? Or, do we have to use this language? Maybe you get a break here on this. I don't know. But from the right means you're approaching 3 from the right. So it's down here on the bottom, and it's like, how far down are you going? Forever.
To
Negative. Yeah. And that is your middle behavior.
Okay.
Yeah. You could ask your instructor about what is the beginning behavior. All right. All right, let's see what we can get done on number 2. We'll get enough done now. Full disclosure, you can go to Desmos and graph these and find all the information we're doing. So if we don't get done with everything, please use those resources. I know they don't help you on the exam, but it's worth checking out. So the numerator is actually a perfect square trinomial. You figured that out already, x minus 1, x minus 1. And the denominator, you have to first factor out the greatest common factor. So it's okay to do this in pieces. I know that we would love to just get it all in one step, but sometimes you can't. All right, now I know we did domain first. We're not going to do domain. There are no holes because there is no place where the factors in the numerator and denominator cancel. So we're going to move right to vertical asymptotes or discontinuities. And there is more than one because you're setting the denominator equal to 0. So you're setting x minus 3 equal to 0 and x plus 3 equal to 0. So x is 3 and x is minus 3. And these are the equations of your discontinuity. Now, do you have to graph number 2, or is that just on another page?
I do have to graph number 2.
Okay, so I would immediately graph those. Be like, all right, let's get those down. So minus 3 plus 3, there they are.
Got it.
Okay, now to do the horizontal asymptote or the end behavior, the horizontal asymptote, you got to figure out which case it is. And it's actually easiest to go back to the original and look at that. I know I said you generally don't go back to the original, but this one didn't reduce, so we can. So the degree of the numerator is 2, the degree of the denominator is 2. So it ends up being 1/2, 1/2, ratio of the 1/2 there. And you're supposed to do this, as x goes to infinity, or do this limiting stuff, but we're really running out of time. So let me just jump right to that. So you graph that right there. Boom, you got that. Now, I mentioned that you can't cross these dashed lines. That's only true in the extreme edges. In the middle, that's not true. So there's actually no dashed line here, although I like drawing it, but there is no dashed line there.
Okay.
But I would still draw it. Okay, y-intercept. Y-intercept is when x equals 0. So you can notice it's just the last two terms. It's -1/18. Boy, that's not that great. That's right there. -1/18. And then x-intercepts, you're setting the numerator equal to 0. You're setting x minus 1 and x minus 1 equal to 0. They happen at the same place when x equals 1. There's that. Okay. And then to do the rest of this, we don't have time to do it, but you'll see that this ends up snaking.
Okay.
I think. No, it does not, because it touches there. I believe it looks like this, but please check that on Desmos.
Okay.
Sorry, we ran out of time. Just couldn't quite
That's
get to
okay.
anything. The middle behavior is around this stuff right here. So you actually have to do 2 equations.
Okay.
We could definitely, work on this again next time. So if you do schedule another lesson, we can just pick up right here. Otherwise, that is it for tonight. So thanks for letting me help you, Paige, and
Yeah.
we'll see you next time.
Thank you. See you next time.
Okay, bye.
Bye.